Have you ever wondered why water droplets spread out on glass and most metals, but beat up on other surfaces like the leaves of a plant? Why do some surfaces like Teflon repel water, and even some surfaces like wax paper as well? The answer lies in the relative hydrophilicity of the surface, which can be quantified by the surface tension of the fluid in the solid surface as a function of the contact angle. A droplet of fluid on a solid forms a three-phase contact point, which is characterized by the surface tension for the liquid in equilibrium with its own vapor, the surface tension for the solid in equilibrium with the vapor of the liquid, and the surface tension for the solid-liquid interface at equilibrium. The angle between gamma LV and gamma LS is known as the contact angle theta, and it provides a rough estimate of whether a particular surface is hydrophilic or hydrophobic. For the reference fluid of water, a surface can generally be considered hydrophilic if it has a contact angle less than 90 degrees, indicating good wetting, and hydrophobic if the contact angle is between 90 and 180 degrees, indicating poor wetting. This value is not a direct cutoff, however, as certain changes in the contact angle are good enough to determine actual surface and fluid changes. The contact angle is related to the surface tension by the Young-Dupré equation, and while theta can be measured directly and gamma LV can be attained from literature data, this still leaves us with two unknowns to solve for. Solving for the surface free energy requires relating this interfacial surface tensions to either an empirical equation of state or by dividing the interfacial surface tensions into separate interactive force components. The second approach draws upon an understanding of the molecular origins of surface tension, whereby differing dispersive, polar, hydrogen bonding, and acid-base interactions between the fluid and solid determine the relative attraction between the two substances. For instance, glass is easily wetted by water and considered hydrophobic due to its typical surface composition, which forms favorable adhesive hydrogen bonding interactions. Only considering dispersive forces leads to a geometric mean simplification, which can in turn lead to the calculation of gamma SV through algebraic rearrangement. But what happens when different additives are added to water? We hypothesize that salt will strengthen adhesive forces within a water droplet and increase the contact angle even on hydrophilic surfaces, while conversely soap should disrupt the surface tension in the air and decrease the contact angle even on hydrophobic surfaces. The contact angles of water, salt water, and soapy water on wax and glass paper respectively were determined through camera images overlaid with a protractor to determine the actual angle of each image. The contact angle of plain water and glass is lower than on wax paper by approximately 25 degrees. This observation fits with our knowledge of glass being more hydrophilic due to its favorable polar or more specifically hydrogen bonding interactions, as opposed to the long hydrocarbon dispersion interaction dominant on wax paper. The contact angle increased for salt water on both glass and wax paper, indicating that our first postulation that the adhesive forces within water due to more charge group interactions would increase was reasonable. The contact angle was decreased for soapy water on both surfaces, also proving our second conjecture that the hydrocarbon chain addition to water would disrupt the liquid-air surface tension and cause greater surface wetting. While the solid-vapor interfacial tension was also calculated, the values varied widely in no small part due to experimental and mathematically introduced errors. First, the contact angle measurements were not all taken from perfectly horizontal angles and with the smallest drops possible. This introduces perhaps the greatest error, since small variations in the angle result in large deviations in calculated surface tension due to the square root term. The geometric mean simplification itself for dispersive forces was also imprecise, given its neglect of the polar, hydrogen bonding, and acid-base interactions inherent to water. The literature value for the surface tension of water and air also only fully applies to the water-only system, and even then only really to deionized water, since additives should change the partial vapor pressure and this surface tension value. Despite these errors, our experiment demonstrated that different additives will change the surface tension and apparent hydrophilicity or hydrophobicity of a solid surface, which can be useful for anything from needing to clean off the surface or treat something to make sure that water stays on it or does not.